Hi, today we're going to look at section 6.9, which involves integrands involving a quadratic and also using long division for integration. Sometimes our techniques of just letting u be something um, doesn't lead to results that we can actually do the integral. And so there's other techniques, and these are two of them that we're going to look at today. Um, First of all, we'll go back to involving the quadratic. We do what's called completing the square. Now, you guys, if you search your memories, will remember that you did that in Algebra 2. Um, and so we're going to kind of review an example of that. If I have something like x squared plus 6x minus 11, let's say, and I wanted to try and write that as something squared. Well, you really can't, because to complete the square, uh, this doesn't work in this case. What I want to do then is make it so this part becomes part of a perfect square like that. And the technique of that, let me rewrite that over here. The technique of that is taking half of this term right here. So 1/2 times 6 is equal to 3, and then I square that. And so what I'm going to do is rewrite this as x squared plus 6x, and then I usually just put a little plus blank in here, minus 11 on there. And this is what I'm going to put in that blank right there, is what half of this term squared is. So I'm going to add 9 to it. But we can't just add 9 in here. These two things aren't the same thing then. To balance it out, what I'm going to do is minus 9 over here. This part right here now is what's called a trinomial perfect square, and it can be written as x plus half of this term, 3, what you got for that, squared, and then minus 20 over here when you combine these two things together. But whatever you add in here by taking half of this and squaring it to make this be a perfect square, you have to make sure you subtract it over here. This is now written as a perfect square minus something or plus something. And that's the goal we want to have. The idea is, most of it, we're going to use the fact that the integral of du over u squared plus a squared, there's a form that's written, and it is 1 over a, the inverse tangent of u over a plus c. So that's the formula that we're going to be using on most of these problems today. It's dealing with the inverse trig functions is what they deal with. It's a matter of matching this up to our formulas for that. So as an example, let's look at this problem. Let's look at the integral of dx over x squared plus x plus 1. I want to complete this square right here. This can't be written as a quantity squared like that right there. So what I want to do is rewrite it that way. So I would write dx over, and I want to complete this square. So this middle number here is a 1. So I would go half of 1 is 1/2, and 1/2 squared is 1/4. So I would write it as x squared plus x plus 1/4. And then it's got the plus 1 here. But I added a quarter, so I have to subtract a quarter. So now this can be written as the integral of dx over this part right here is my trinomial perfect square. It can be written as x plus half of this term, 1/2, squared, and then 1 minus 1/4 is 3/4. Once you have this, the key is let u equal this part right in here. So u is going to equal x plus 1/2. du then is equal to dx. So this integral up here, just kind of separating that, becomes the integral of du over u squared plus, and I want to write this to match this up to this form up here. I want to rewrite this as something squared. So I'm going to take the square root of it. So it'd be the square root of 3 over 2 squared. And now this is exactly in that form. And so it's really a matter of just matching up, what do I have? So this is going to equal 1 over a, with a being, this is a right here. So it's 1 over square root of 3 over 2, the inverse tangent of u over square root of 3 over 2 plus c. And don't forget the plus c. Now, simplifying it a little bit, when you divide by a fraction, you invert it and multiply. So this is really 2 over root 3, the inverse tangent of u. Well, same thing here. It would be 2 over root 3 u plus c. But we don't want it in terms of u. We want it in terms of x. So we make this substitution back in for u. And you can rationalize the denominator. So I'm going to multiply by root 3 over root 3. So this would become 2 root 3 over 3, the inverse tangent of 2 root 3 over 3 times x plus 1/2 plus c. And there would be your answer. Now, if you have questions on that, I'll have a Zoom open during class and you can ask me about that. Another example then, excuse me, that can happen is if we had a problem like this. If we had the integral and there was an x on the top. And we'll just leave the same thing on the bottom. Okay. And what you do is you try, because there's an x up here, it's a little different than the previous problem. Basically, it's the same problem as I did here, except there's an x up here now. And in that case, sometimes you can do a little trick of, you want to try and make this numerator be the derivative of this part down here. And so if I were to look at x squared plus x plus 1, the derivative of that is 2x plus 1, right? So to make this up here become that, the little trick is I'm going to multiply this by 2, and to balance that out, I'm going to put a 1/2 out in front. So it's still just x over that. And then I want to get this in here. And so what I'm going to do is rewrite it as 1/2 the integral of 2x. I'm going to add plus 1, and then I'm going to minus 1 from it. So I haven't changed it any. I've just manipulated it so now that I have the derivative of that on the top. Now I can separate this into separate integrals. So I'm just going to write it as 1/2, and I'll just leave the 1/2 out in front. It's the integral of 2x plus 1 dx over x squared plus x plus 1 minus the integral of dx over x squared plus x plus 1. our first example was doing this, and I did that on purpose just so I didn't have to go through that all again and take up the time to do it. So what we're going to do then is now, if I let u be this part down here for this first integral, so this is going to equal 1/2. I'm going to let u equal x squared plus x plus 1. Then du is 2x plus 1 dx. That's what I have right here. This is du, and this is u. So this is 1/2 the integral of du over u, and then minus, and we're going to use what I got as my example over here. If this was just a different problem, you'd have to go through and work this out, which we just did. So what I have is let me copy that down there. We got 2 minus, and we got 2 root 3 over 3, the inverse tangent of 2 root 3 over 3 x plus 1/2 plus c. Okay. So now the integral of du over u is just the ln of u minus 2 root 3 over 3 inverse tangent of 2 root 3 over 3 x plus 1/2 plus c. Can't forget the plus c on the end. Last thing then is to substitute u back in here. So I get 1/2 I'm going to multiply through by the 1/2 too. So it would be 1/2 the ln of x squared plus x plus 1 minus, if I take half of this, that would just be root 3 over 3, the inverse tangent of 2 root 3 over 3 x plus 1/2 plus c. And that would be your answer then. And it's not an easy technique, but sometimes that's the only one that does seem to work. So that's what you try to do. Okay. Now what we're going to do next then is look at the second example of, or second thing in this section technique is called integrating an improper rational function using long division. Something like this is the integral of x squared over x minus 1 dx. Improper rational function is one where the numerator has a higher degree than the denominator. That's called an improper rational function. And what you do is you go ahead and you use long division to solve that. So I'm going to take x minus 1 and divide it into x squared. When I taught this, I always made sure I had place values for all of the parts. So I just put, if it's missing, like there's no x in here, I put 0x. There's no constant, I put 0. For long division then, what you do is you take this term and divide it by this one. So I do x squared over x. Well, that just equals x, and I put that up there. Division, you multiply x times x is x squared. X times -1 is a minus x. Now you subtract. Well, subtracting is adding the opposite. People usually miss the signs. So I just say at this step, when you go to subtract here, just switch all of these signs in this thing you multiplied out. This becomes minus and this becomes plus, and then you add. And that cancels out. I get x plus 0. And then I do it again. X divided by x. Take this and divide it by this. The leading term dividing by the leading term. X over x, which is just equal to 1. So it would be plus 1. 1 times x is x. 1 times minus 1 is minus 1. Change the signs and add, and I get 1. So I would write it then as the answer is x plus 1 plus 1 over x minus 1. So this expression can be written like this. So now what I have is then this becomes the integral of x plus 1 plus 1 over x minus 1 dx. And I can break that into separate integrals. So I can write that as the integral of x dx plus the integral of 1 dx plus the integral of 1 over x minus 1 dx. Well, these two are pretty straightforward integrations. Integral of x dx is x squared over 2. And we'll keep the plus c till the end after we do the integration for all of these. The integral of dx is just x plus c. This one I have to do a u substitution. I'm going to let u equal x minus 1, so du equals dx. So this becomes plus the integral of du over u, which we figured out before. Integral of du over u is the ln of u, and there's my plus c at the end. Last thing is we'll substitute that back in there, so it becomes x squared over 2 plus x plus the ln of x minus 1 plus c. And that is your answer. And that's how long division works. Okay. Again, I'll have a Google Meet open during class for you to ask questions on it. Hopefully, I'll be back on Thursday. Have a good day. Work on it, and we'll work on it when I get back.